Hi, everybody, and welcome back. So last time we talked about using for loops to perform a sequence of calculations, and we said that the main strength of using the for loop was that you can perform calculations at one instance in this sequence that depend on the calculations previous. And vectorized computing, it's very challenging to do that with vectorized computing, but it's much easier to do that with for loops. So if you end up having to do a calculation where the decision that you make or the computation that you make at one instance of time or one instance in a sequence depends on something that happened in the past, that's where a for loop is going to be very strong. The while loops and then the break statement. Notice that for loop doesn't come with a break. The reason that a for loop doesn't come with a break is that you specify ahead of time how many computations that you want. So back here, I had to set ahead of time that I wanted 50 numbers calculated. And I said, okay, give me from 3 to 50. So I'm telling the computer, hey, computer, you need to do this 50 times, or technically this would be like, what, 48 times from 3 to 50. The while loop, however, does not have that restriction. The while loop will keep operating until the heat death of the universe or until your computer turns to ash, or basically until you stop it. Okay, so that's why I have in bold here, use while loops with extreme caution, because if you don't write them appropriately, they can literally just run forever. And then you basically have to force quit R or power down your laptop or whatever to get it to stop. Um, so be careful with this. Be aware that while loops are very powerful, but they come with great power comes great responsibility, as Uncle Ben says. So the thing the thing about a while loop is the while loop will continue to perform an action until a certain condition is met. Or if you and realistically, every time you write a while loop, you should have a break statement in there just in case you never perform that action. So what you're going to do is you're going to say, okay, I want you to continue to perform this action um, and until one of two things happen. Number one, until you find the answer that you're looking for, or two, until you've been at this for like 3 or 4 hours. And if you, after 3 or 4 hours, you still haven't found the answer, just stop. Okay, that's what the break statement is saying. Um, so while loops are actually the foundation for most mathematical algorithms. Mathematical algorithms operate until tolerance is achieved. So there's this mathematical concept called tolerance, and that is like in numeric methods where you say, keep performing this action until you get close enough to the right answer. Okay. Now, close enough for a human and close enough for a computer are very, very different things. We would say like, okay, if the right answer is the number one, if you see a person, like we're expecting that you just to get the number one, but computers, whenever they work with operations, they're actually dealing, if you remember back to this, they're dealing with like 16 decimal places worth of information. Um, so what is the difference between the number one and the number 1.00000000003? Like something out at like the 11th decimal place. If you ask a human, they'd be like, those two numbers are one. Like that's a one and a one. We're talking about something at the 11th decimal place. Okay, like a hundred billionth or something. For a computer, though, you actually have to tell it that making a mistake in the 11th decimal place is okay, because otherwise the computer is just going to say, well, I have one and I have 1.0000003 or something. Those two numbers are not the same. Whereas a human would say, yeah, they are. What's the problem? So while loops will use a break statement to say, as long as you're within a tolerance. Now, the tolerance has to be set by a human. The human would say, okay, if you're within 8 decimal places of each other, then you're correct. Okay. So if I have a 1 and I have a 1.00000000005, okay, that 5 happens at like the ninth decimal place. Therefore, for the first 8 decimal places, I've got zeros. So if I compare the first 8 decimal places of the number, I have the number 1, and then I have another number that is 1 with 8 zeros after it. then the tolerance, if you set the tolerance at the 8th decimal place, then you say those two values are the same. So that's what we're getting at here, that a computer will keep going until numbers are literally exactly the same, because computers don't understand like gray areas. There's actually an entire branch of mathematics called fuzzy logic that tries to give a computer the ability to make these sort of gray area decisions that humans are super good at. Like a human will look at the number one and a number 1.00000000005 and be like, those two numbers are the same. What's the problem here? But a computer will not. A computer naturally does not operate on fuzzy logic where humans do. Humans are allowed to kind of like blur the edges, and we're good at it. That's one of the things that our brains are good at doing. So anyway, let's get into an example here. We're going to use a while loop to figure out if Todd, a software developer, can get a date. Okay, so we're going to say that we have to initialize the while loop, just similar to the way that we had to initialize a for loop. So if you remember, for the for loop, we had to create a vector to start off with. So we created an empty vector to store our results. And we said, well, we know we're going to do 50 computations, so we're going to create an empty vector of length 50 and then initialize it. Similar for a while loop. The issue, though, is we can't, it's difficult to initialize a while loop because we don't know how many computations we're going to need. Okay, so usually the initialization of a while loop is a little bit different. And that is, we just get two atomic vectors here, and we say, just count the number of attempts so far. So the first thing is set has date equal to 0 or false or something, and then say while this is true. So while this is not equal to 1. Okay, now right now we start with 0, so clearly it's not equal to 1, so that means that we're going to do something in here. While this is not equal to 1, you're going to draw a single random normal value, and you're going to find out, is this less than 1.96? So we know that this happens with 2.5% chance. So I'm not, I'm as a like a somewhat of a software developer, I know that sometimes we can be a little socially awkward. Okay, sometimes we don't quite pick up on social cues, and so maybe it would be a little bit harder for us to get dates. So we've got a software developer, and we're giving him a 2.5% chance to get a date at this speed dating event or whatever. So each time we're going to draw a random number, and we're going to say, okay, is this less than 1.96? So this is a success. He would, if this is true, so this is, because we're going to see this is either going to be true or false. And then what we're doing here is we're going to say, okay, is this true? If it's true, then we're going to stop, because this thing would be equal to 1. Okay. If it's not true, or it would be equal to true, if you will, but true gets promoted to 1 because it's being compared. Do you remember your type coercion from the atomic vectors lesson? So we're starting off with numeric here. We're performing a logical comparison, but then performing another logical comparison between this numeric, or this is actually a logical, and this is a numeric. So this logical gets promoted up to numeric. And so true gets promoted to 1, false gets promoted to 0. So if this thing ever turns into a 1, then the while loop will stop. Now, one of the other things that we want to do is we don't want this to just keep running without telling us what it's doing. So we're going to keep track of how many dates Todd has been on in the speed dating scenario. And so each time we draw, we give ourselves, we roll the dice to see if Todd hits it off with this date, we add 1 attempt, okay? And then we're going to keep track of the attempts. We're going to print them so that, and you remember from the exercise that you did before, we need a print statement here. Otherwise, we can't see inside the while loop. We can't see inside these curly braces while the condition is working, okay? So you see here, Todd goes on quite a few dates. He gets up to 60. The while loop repeated 60 times. Now, for you, whenever you run this code, you may get Todd a date just inside and with 5 dates, okay? Because this is random. This is a random normal condition, okay? Now, if we say, all right, well, 60 is a lot of dates. What if we don't even have 60 dates? Or what if Todd is getting discouraged by this point? So let's say that Todd promises his family that he will go on 30 dates. So if he keeps going and he's about to hit the 30th date, and if he still hasn't found a date at the 30th encounter or whatever, then he's going to exit from the event. So in this case, we're going to have a break statement. Okay. So notice this, the code up here is the same. The print statement is the same, but we're going to add some code right here in the middle. And we're going to say, okay, you're keeping track of attempts. If attempts get to 30, then we're going to print a message that says we did not find a date, and we're going to break the while loop. We're going to escape so that we're not running this forever. We're not having Todd just keep going around the room frantically and searching in futility for a date. We say, okay, we've met 30 people, didn't hit it off with any of them. Let's go. All right, let's go get a cheeseburger and a milkshake and go home. All right, so now when I look at this, when I run this, I'm printing all of these and I get to date 29 and I see that by date 30, we still haven't found a date. So we print the message, nope, we didn't find a date. Okay, again, notice, however, though, this is 29 atomic vectors of length 1, atomic integer vectors. This is, actually, they might be numeric because I didn't add an L. Yeah, they're going to be numeric. This is an atomic character vector. This is our message out. And we've said, okay, we did not write a for loop. Oh, okay, so I'm going to talk about this exercise, but I'm going to go here first. When you typed these things, notice that while turned a different color. It might have turned bold. It might have turned a different color in your computer. So here's while looks different. For and in look different. And then if and else look different. Okay. And the reason for this is because they are reserved words. That means you're not allowed to modify them. Okay. They are so fundamental to how R actually does what R does that they are reserved and they are kept sacred, and you, the programmer, are not allowed to touch these commands. Okay. The reason why is because everything in R is built on top of them, or basically. They're either built on top of these 5 commands, or they're built on top of the C++ or C or Fortran versions of these 5 commands. You are not allowed to mess with these, okay? Because if you do, you will literally break the computing language, okay? So you don't touch these things. All right, now let's leave you with a homework assignment before we get into functions, okay? So think about what would happen. How do you stop a while loop that you didn't include a break statement in? Like how would you do that? And then read through this lesson on decisions and loops, so that you can kind of wrap your head around a little bit more of what's going on here. Okay. All right, and we will stop it here. The next lesson, we're going to talk about functions and why functions are like why we usually prefer to use functions instead of while loops, for loops, and some of the other stuff like that. Okay, see you soon.